Yes, ma'am, we are live as well.
Okay, so we'll start. So welcome students to this evening of learning physics with conceptual and problem-based approach organized by the National Academy of Sciences, India, NASI, Delhi chapter, an 11-week course which started on 27th of July 2020, every evening from 5 to 8 p.m. And we are also right now live on the YouTube channel of NASI Delhi chapter. Me, along with my co-convener, Dr. Pushpa Bindal, and the organizing team invite you to enjoy learning physics, molecular physics today. And today's subject being molecular physics, we have two speakers. The first speaker will be Professor Bhas Bapat, and the second speaker will be Dr. Vaibhav S. Prabhu Desai. Professor Bhas Bapat is Dean Academics and is working at Department of Physics, Indian Institute of Science, Education and Research, Pune. So Dr. Varsha, please, the second slide. Yeah. Ma'am, I shall have the pleasure of introducing the speaker.
Sure, sure.
So, Professor Bhapat is working at present, as I mentioned, in the Department of Physics, Indian Institute of Science, Education and Research, Pune. He did his master's in 1992 from IIT Bombay and received his PhD degree in 1997 from Tata Institute of Fundamental Research, Mumbai. His PhD thesis was on two electron processes in collisional ionization. He completed his postdoctoral fellowship in 2000 from Freiburg, Germany, on the topics recoil ion momentum spectrometer, electron beam ion trap construction, spectroscopy of HCI. He has research experience of more than 20 years. He has worked at PRL Ahmedabad from 2002 to 2014, where he did molecular fragmentation studies using electron beams, synchrotron radiation at Indus 1, RR Cat Indore, and ion beams IUAC since 2014. He is working at ISA Pune. He researched on orientation dependence in ionization of molecules by ion and electron impact molecular ionization and fragmentation in intense laser fields. Currently, he is working on a new project for studying slow ion molecular collisions approaching non-perturbative, non-Born Oppenheimer domains. He served several administrative responsibilities at ISER and has helped establish and mentor ISER Tirupati as dean also. He has been Dean Academics at ISA Pune since 2018 June, and 6 PhDs have been awarded under his guidance so far. So welcome, Professor Bapat. It's a pleasure for me to have you here at NASI. And I'm really grateful, along with the rest of my team, that you have agreed to deliver a talk on molecular physics. And as I say, that when a person who is doing research in a particular field, when that particular person explains basic physics, then the understanding is definitely different and more enjoyable. So with those words, I welcome you to share your screen and please, yeah, you are unmuted. Yes, you are unmuted. So I request you to kindly share your screen and deliver your talk.
Yeah, welcome, Professor Bapat. We are really lucky to have you here. I'm sure the students are going to benefit from your talk because it will be definitely, influenced by whatever you're working deeply in. So thank you so much for agreeing and kindly start your talk.
So, good evening, everyone. I'm happy to be sharing this platform with you. I can see that there is a large number of participants here. Perhaps all of them are students, but there may be some teachers as well in the audience. It's likely that students are from slightly different backgrounds and levels. So I would like it if we keep this session interactive and students ask questions whenever they feel the need. And the best way to do this would be to write in the chat box rather than talk, because that can be a bit distracting. So Punita, would somebody be keeping an eye on the chat box, or should
Yes,
I do it?
yes.
Yes, sir. Good evening,
Varsha will do
sir.
it.
Yeah, I will do that, sir.
Okay, excellent.
Yeah.
So please please put in your questions in the chat box. And since this is the first time we are meeting, it might take me a little while to judge whether the level is right or wrong. So please excuse me for that. What I'll begin with is to to pose a very simple question to you is, so if you just want to say something like yes or no, it's okay to unmute your mic and mute it back, but don't go on a long rambling note with your mic on.
Pass. We do not allow unmuting the mic
Oh,
because
okay,
it's
okay.
very
So fine,
difficult
fine,
to
fine.
control.
All
But
right. So
anything
just
that they
chat
say,
boxes. Okay.
anything that they say either on YouTube or chat box will be
All right.
conveyed to
Okay.
you
Okay.
immediately.
Sure. So let us simply begin with something that we have studied for a while now. So if you are in your third year of BSc or first year of MSc, you must have at least had this 2 years ago or 3 years ago. The structure of the hydrogen atom, which is the simplest atomic structure for which quantum mechanics gives you exact solutions. So I hope that all of you understand what a solution to a Schrodinger equation means. And you must have also studied the Bohr atom. Now, the Bohr atom is essentially a mix of quantum mechanical and semi-classical or classical ideas, which allow you to describe the energy levels of a hydrogen atom based on some quantization rules, some ideas borrowed from quantum mechanics, like the de Broglie hypothesis. And it then puts in some classical ideas about the field seen by the electron, the classical electromagnetic field, and so on, and manages to put together a picture which gives very accurate description of the energy levels of the electron in a hydrogen atom. Of course, this mix bag of ideas works well in this case, but it doesn't work entirely, in the sense that if you start probing the structure of an atom a little more deeply, such as by doing very high precision spectroscopy, then we find that the hydrogen atom, as described by the Bohr model, is an incomplete description. And the Bohr atom, for example, cannot describe things like the fine structure, or it doesn't describe the so-called degeneracy of certain states or the accidental degeneracy of certain states. So we need to take recourse to full quantum mechanical calculations. And you're probably familiar with the Hamiltonian equation and the Schrodinger equation for the hydrogen atom. Now, if you go to a slightly more complicated system, which is not the hydrogen atom, but the hydrogen molecule, then the situation actually becomes quite complicated. In the hydrogen atom, we have one electron, which is moving in the field of a proton. And the situation is a centrally symmetric centrally symmetric system. The potential energy of the system is described purely by the radial coordinate, the distance of the electron from the proton. So only one variable, the radius, comes into picture, and the potential is symmetric in all directions. It is spherically symmetric. But for a molecule, the situation is quite different. So in a molecule, there are at least two nuclei. So in the case of H2, for instance, there'll be two identical nuclei. But if you have a simple diatomic molecule like carbon monoxide or nitric oxide or HCl or NaCl, all of these are diatomic molecules. And in these diatomic molecules, what you have are these two uh, atomic centers, if you like, which when they are far apart behave like two separate atoms. But the moment you bring them close, what happens is that all of these electrons, which belong to the combination of, say, sodium and chloride, or belong to them together, they start moving in a field that is described by not just one one nucleus, but the field described by two nuclei. So once this happens, you cannot write the potential in any simple form, and you have to then start making approximations. Okay. So in the case of the hydrogen atom, you can write down the Schrodinger equation and solve it in a relatively straightforward manner by separation of variables. But this doesn't become possible, or it is not certainly not very easy in the case of a molecule. And the primary difficulty there is the fact that the potential seen by any one electron is not a radial potential. Okay, so This is true also of a large atom where there are many electrons and just one large central charge. Even there, it is not a central potential. But for any one electron in an atom, the potential is a central potential. In the molecule, even that is not the case. If you take just one electron, even this electron is going to see the potential due to two very heavy positively charged nuclei. So when this happens, we start looking for approximations. Now, what are the kinds of approximations that you can make? So whenever we are faced with a problem which is very difficult to solve, we try and find out what are the limits or what are the ranges of different parameters for which some approximate solutions can be found. Okay. So for instance, when you are doing an experiment in which you are measuring the period of a second pendulum, let's say, then most of the times we make the approximation of small angles. Okay, so which means that if the pendulum is not making very large excursions from its mean position, and the maximum displacement, maximum angular displacement is like say 5 degrees or 10 degrees, then the whole problem of solving the equation of motion for the pendulum becomes very considerably simplified. It becomes a simple harmonic motion in which you make the approximation that sine of theta is equal to theta. So similar approximations are very frequently needed in different branches of physics, and in particular, in the context of the topic that we are discussing today, there is one very important approximation that we make use of. Okay. Now, the main approximation that, or the main sort of simplification that can be brought about in the description of a molecule rests on the fact that in a molecule, these nuclei, okay, the ones that are shown in green and red circles, filled circles, these have very large masses compared to the electrons that are surrounding it. So if you just do a simple back of the envelope calculation, then in a molecule like say sodium chloride, this nucleus is about 10,000 times heavier than the electron. In a hydrogen atom, it is about 2,000 times as heavy. Okay, yeah, nearly 2,000 times. So the point is that there's a huge difference in the masses of the nuclei and the electrons. Now, what do you do when you have such a situation? Let us go back to the case where we are describing the motion of the moon around the sun, moon around the earth, or the earth around the sun. In the crudest approximation, what you can do is you can assume that the sun has an infinite mass and that the earth is a point object moving around going around the sun. So in this case, you get perfectly circular trajectories. And if you relax this very strong, very simple approximation that or very crude approximation that you have made, you start getting various things like the Kepler orbits, and you have to then start worrying about moving to the center of mass frame, which does not coincide with the center of the sun. So all these things are known to you. So similar approximations need to be made in the context of molecules. The approximation of the most important approximation that we make rests on the fact that the masses of the nuclei and the electrons are very different. So when this approximation is made, what we can then work out is that, see, if the field due to these two heavy particles is known, then you can describe the motion of these light electrons in the field of these two nuclei, and not worry about how much these heavy particles are moving, because these particles are going to move very slightly during the time in which this electron will move. A light particle will move faster in a field compared to a heavy particle. Okay, so they are all experiencing the same field, okay, but these being light particles, they will move faster. Now, once this approximation is made, you get what are called a potential energy description or a potential energy picture of a molecule. And we start distinguishing between different types of energies or potential energies in the molecule. So there's a rotational potential energy, there's a vibrational potential energy, and there's an electronic potential energy. So the rotational potential energy is basically these two heavy particles going around each other, very much like a sun and a planet system, except that these two masses are usually not very different. They may even be the same. Okay. Then comes the vibrational potential energy, And the vibrational potential energy corresponds to the repulsion between these two particles, the heavy nuclei. But these are both positive charged particles. So in principle, they should just fly away. But the overall neutrality of this system ensures that if these two particles tend to go far away, the electrons pull them back because the electrons are negatively charged. So there is this vibrational motion in which these two particles keep moving away from each other along the line joining these two. So that is your vibrational degree of freedom. Then the third component of your energy, or the third degree of freedom, is the electronic degree of freedom, where these electrons are free to move in the potential of these two, and is the energy differences between different eigenstates of these electrons. So eigenstates might be something a bit unfamiliar or uncomfortable for some students. But let's say that the energy levels of the electrons are much more widely separated than the energy levels because of the rotational or electronic motion. And then once you separate these two, then the net energy of the molecule can be conveniently depicted in this fashion. What you do is you assume that all motion is happening at a particular internucleus, or sorry, all electronic motion is happening at a particular internuclear separation. And if you change the internuclear separation, the change in the energy of the electronic system is very small. So small changes in the internuclear separation do not change the electronic energy, they only change the nuclear or the internuclear energy. Once that happens, you start getting curves like these. Okay, so this solid curve over here describes the total energy of the molecule as a function of internuclear distance for a specific electronic configuration, namely here the ground state. The excited state, which is a new state, new electronic state, has a potential energy curve which has a different shape from this. Okay? Typically, it has a minimum which is at a larger distance than the ground state, and it is also generally broader. Okay? So this is an excited state. So in the case of atoms, we do not have these kind of detail. I'll just sketch something on this so that it will become a little easier for you to follow. So in the case of atoms, we are used to drawing energy levels such as, let's say, just a level here, and then maybe another excited energy level here, and maybe a third excited state, which is here, and a fourth excited state, which is maybe here. So these four energy levels are simply levels in the energy domain. So E0, E1, E2, E3. And these are arranged according to the value of the energy. You go to higher energies, you just simply draw level up. In the case of molecules, however, these energy levels are a function of the internuclear distance. So in some sense, if you like, you can think that these are horizontal lines, but in the case of molecules, these are not horizontal lines, but they are curves with minima. Okay. And these minima correspond to the equilibrium separations. So the minimum of this potential corresponds to some internuclear separation, which is the minimum bond length of the molecule. The minimum for this excited state corresponds to a higher energy level of the molecule, in which the bond length has increased slightly. Okay. And similarly, you can have further excited states and so on and so forth. Okay. So now if sorry, I'll turn off my pen. Yeah. Okay. So let us now begin with a little more formal description. And you'll soon see that in this formal description, whatever we just discussed in a very hand-waving argument can be very nicely understood, and it will lead us to solving the Schrodinger equation for very simple molecules like the hydrogen molecule or basically only the hydrogen molecule. Okay? So I believe all of you are familiar with the Hamiltonian. So maybe I can just look at the chat box to see if there are any questions. Uh,
No, there are none as such till
okay,
now.
okay.
And they have had a full course of quantum mechanics with several numericals also. They are
Okay,
well versed
excellent,
with Hamilton.
excellent. Okay, so let us start by writing down the Hamiltonian for a diatomic molecule. Now, remember whatever we have discussed so far is only for a diatomic molecule. We are not going to look at polyatomic molecules at all, okay? Because polyatomic molecules would be much harder to describe, although the principles are the same. We will focus only on a diatomic molecule, and we'll start by trying to solve the Schrodinger equation. Now, the Hamiltonian for a diatomic molecule can be thought of as composed of three terms. Okay, so here is one term which I call Tn, which is the kinetic energy operator for the nuclear motion. Then there is the kinetic energy operator for the electronic motion. And then there's a third operator, which is the grand potential operator. A potential operator which consists of all electrostatic interactions between the electrons and the nuclei. Okay, so that is my Tn. There's a TL electronic, and there's a V. Now this V, which is the potential energy, is a fairly complicated looking operator. So I'll just spend a couple of minutes to explain what the different terms are. So the first term, now Za refers to the charge on atom A. Zb refers to the charge on atom B. So it could be like for sodium chloride, A would be Na, which has Z is equal to 11, and chlorine, which has Z is equal to 17. Okay. Now, the first term is the potential energy seen by the electrons due to the first nucleus. The second term is the same thing, but due to the second nucleus. Now, as you know, the potential energy depends on the on the separation between the particles. So you have Ri minus Ra, the modulus of that in the denominator. Similarly, you have Ri minus Rb in the denominator for the second term. The third term is really what is called, sometimes called the correlation energy, which is just the potential energy due to the electrons interacting among themselves. There's no nuclear term here. So the charge of the electron is 1. So the total electrostatic energy due to electronic interactions will have terms like 1 upon R12 plus 1 upon R13 plus 1 upon R14, all the way to whatever number of particles there are, and various other combinations thereof. So in a compact manner, it can be written like this. You can write it as a double sum of terms like 1 upon Rij and the modulus of that. The last term is this term, which represents the internuclear repulsion. So it is simply the charge on the first nucleus multiplied by the charge on the second nucleus divided by the internuclear distance, or what is usually called the bond length. Okay. Now, in writing this operator, we have made use of what are called atomic units. Now, for those of you who are not familiar with atomic units, uh, don't worry too much. It is just another way of writing a set of units in which h cross is taken to be 1, mass of the electron is taken to be 1, and the charge on the electron is taken to be 1. Okay. So actually not 1 minus 1. I should have been more careful. It is minus 1. So if we put these units, then all our terms for the electrons, which are like h cross squared by 2m, which would appear here, or terms h cross squared by 2m for the electrons appearing here, and h cross squared by 2m for the nuclei appearing here, would not have this h cross. It will just be 1. So it will look like half in this case and 1 upon 2m in the other case. So this is just a way of simplifying the equations. It just saves a lot of space. And actually, it also gives you a more you get a better feel for what kind of energy levels you're talking about. Because if you put h is equal to 1, me is equal to 1, and E is equal to 1, then the energy of the ground state of the hydrogen atom turns out to be minus half. The binding energy, which you all know is 13.6 electron volts in standard units, becomes minus half in atomic units. So if you do all your calculations in atomic units and you find that the binding energy is minus 1, you quickly know that, okay, this is like doubly as strongly bound, twice as strongly bound as the hydrogen atom. So it's a very convenient set of units to do all your calculations in. Okay. Now there is another very peculiar thing that one has to worry about in the case of molecules. Uh, if you remember right at the beginning, I said that the potential that is seen by the electrons in a molecule is not centrally symmetric. So all your rules about angular momentum conservation, etc., break down, because angular momentum conservation rules apply only to a central potential. And if you don't have a central potential, then the grand angular momentum is not conserved. It is possible that some component of the angular momentum gets conserved, depending on the symmetry of the system. And in the case of a diatomic molecule, where there is a cylindrical symmetry. So if you take as z-axis the line joining the two nuclei, then the projection of the angular momentum along this axis will be a conserved quantity. So essentially you are talking of a cylindrical symmetry. So the z component of the angular momentum is conserved. So this Lz, which is written over here, is a conserved quantity for diatomic molecules. Okay, so this is for the electronic motion projected on the internuclear axis. Now, depending on the values of Lz, which are quantized, different electronic states are classified based on their angular momentum, very similar to the case in atoms. In atoms, let's say you go back to the hydrogen atom, then the ground state is a 1s state, the first excited state is a 2s state, then the first excited state also has a slightly higher state called a 2p state, which has a different angular momentum value, but the same principal quantum number. Okay. So just as you have these 2s, 2p, or 3s, 3p, 4f, 4d, whatever, these kind of angular momentum states in an atom, you can similarly have different angular momentum states in a molecule, but those angular momentum states refer to quantized values of the projection of the angular momentum, not the entire angular momentum. Okay, so these electronic eigenfunctions are simultaneous eigenfunctions of the Hamiltonian and the angular momentum projection operator. Okay, so the Lz component, not the full L angular momentum. So because it is a simultaneous eigenfunction of the Hamiltonian and Lz, we will have two different uh, quantum numbers, for which the wave functions are simultaneous eigenstates. Okay. So these quantum numbers are called the angular momentum quantum numbers and are denoted by the letter lambda. Okay. So if lambda is equal to 0, which means if the projection of the net angular momentum of the electrons projected on the internuclear separation has a 0 value, then it is called a sigma state. If the value of the projection is 1, when I say 1, it means 1 in h cross units, so it is h cross. It is called a capital pi state. If the angular momentum is 2, it is called a delta state. If it is 3, it is called a phi state. Okay. So this is very similar to s, p, d, f orbitals in an atom. Okay. And usually one doesn't go above 4 because these molecular states are very complicated and it doesn't make sense to classify them beyond a certain point. Okay. Now, there are other symmetries in the diatomic molecule. So if your diatomic molecule is a homonuclear molecule, there are more symmetries. But there are some very obvious symmetries in any diatomic molecule. So one is that if you do a reflection operation in a plane that contains the internuclear separation, the z coordinate of any wave function or any particle, any electron remains unaltered. Okay. So any reflection in the xz or yz or any plane any plane that contains the z-axis as the symmetry axis, if you perform a reflection operation, then the electronic Hamiltonian doesn't change and the Lz value also doesn't change. And in this case, if your wave function changes from phi to phi prime, then these two wave functions are different only in the sense that the eigenvalue of Lz will be flipped if lambda is not 0. So it's just a change in sign of the projected value. Okay. Now, if the sign of this lambda changes, which is what will happen if lambda is not equal to 0, and the energy also does not change, then these states are degenerate. So just as your I mean 2s and 2p states in the hydrogen atom are degenerate, I mean degenerate to a certain level of accuracy. Similarly, you will have these different angular momentum states degenerate if the states have this symmetry. Okay. So if for sigma states, which means lambda is equal to 0, the wave function is not going to be affected at all because the angular momentum is indeed 0. So any reflection is going to only change the sign of is only be a multiplying factor with the sign unaltered. And this constant has to be only sorry, the sign can be altered, but this constant can only be 1. So there must be two kind of sigma states, and they are called minus and plus sigma states, depending on how this sign changes under a mirror reflection in one of the planes that are described here. So it is like saying that if I have a plane here, and I flip my coordinate system in such a manner that what is up becomes down and what is down becomes up. And if the projection of the angular momentum in an axis contained in this plane is 0, then really nothing changes. This wave function can just pick up a phase which is -1. And if it picks up a phase which is -1, it's called a sigma minus state, otherwise it's called a sigma plus state. Uh, Now for homonuclear diatomic molecules, uh, there is what is called an invergence symmetry also. Okay. So an invergence symmetry is essentially a higher order symmetry than the reflection symmetry. So in the reflection symmetry, we were just taking a reflection around a plane in a plane, which means that the azimuthal angle is changed from phi to 360 minus phi, okay, or 2 pi minus phi. But in this case, we are talking of a higher order symmetry where the entire radius vector or entire position vector is flipped. Its sign is changed from r to minus r. If such a symmetry is obeyed by this, I mean, is possible in the case of a homonuclear diatomic molecule, and this is in principle not going to change the molecule at all. Whether you hold the molecule like this or you hold the molecule like this, it is still the same molecule. But that is not true if this is say Na and this is Cl. Then if I change R to minus R, I'm going to get a different molecule in this sense. Okay. So this kind of an invergence symmetry is present only in homonuclear diatomic molecules, and flipping the sign of R uh, doesn't change the electronic Hamiltonian. It doesn't change the LZ operator. So if with this change in phi, what is going to change are some angles, and if the wave function that results out of this change of r to minus r, if it picks up a sign, then it is called if it flips sign under an inversion, it is called an ungerade or an odd state. Or if it doesn't flip a sign, it is called a gerade or an even state. Okay, so this is gerade and ungerade are just German words for even and odd. So
Sir, there is a small doubt if
yeah,
yeah, this is from Arya that sir here sigma delta etc is equivalent to SPD or just they have a similarity.
there's a similarity because see, SPDF relate. I mean, so in the case of a spherically symmetric potential, the L squared and LZ both operators are conserved. I mean, are simultaneous eigenfunctions of the Hamiltonian. The same wave functions are eigenfunctions of L squared and LZ also. In this case, in the case of a molecule, L squared is no longer conserved. Now, L squared is not a good. I mean, the L plus one is not a good sorry, not a good quantum number. But Lz, which corresponds to the projection of the net angular momentum on the internuclear axis, that is a conserved quantity, and hence that is a good quantum number. So the sigma, pi, delta, and phi refer to the projection of the angular momentum on the z-axis or on the internuclear axis. It doesn't refer to the net angular momentum. In the case of an atom, it refers to the net angular momentum. In the case of the molecule, they refer to the projection of the angular momentum on the internuclear axis. Okay, so they are only similar, they are not the same.
Thank you, sir.
So the last part that we need to worry about before we start writing down the wave function is about its spin multiplicity. Okay, so if you are talking about a molecule, generally you will be talking about a molecule with large number of electrons, and these electrons have spins, and the way the spins are organized or ordered, you may have a net spin quantum number s, which is the sum of the spins of the electrons. This s, if it is non-zero, then you will have a multiplicity of 2s plus 1, which means 2s plus 1 different spin states are possible for a given electronic state. And if s is large, you will get multiple such levels. And these are again governed by the Pauli exclusion principle: two electrons, one up, one down in one shell, or in one state. So you'll have these 2s plus 1 possible states. Now remember that in the case of atoms as well as molecules, what finally decides the multiplicity is the number of electrons in the open shells. So if there are some shells which are closed, then the net angular momentum of the net spin of those electrons is zero. So they don't contribute to the spin multiplicity. Only the open shells in which there are unpaired electrons, those contribute to the multiplicity. So finally, for a diatomic molecule, you can have different your electronic states labeled by different parameters, if you like, and they're called term symbols. So the first term symbol, the first component of the term symbol is the angular momentum projection lambda, which can be 0, 1, 2, 3, 4. And this corresponds to the symbols sigma, pi, delta, and phi. If there's a reflection symmetry, okay, you can only have a plus minus sign change in case of a reflection symmetry. For molecules in which the projections are, the lambda values are 1, 2, and 3, they don't have this reflection symmetry. In the case of inversion, which is to homonuclear diatomics, you may have additional labels or additional components to the term symbol correspond to whether the inversion symmetry results in an even wave function or an odd wave function. Meaning whether the function changes sign or not change sign. And these are labeled by G or U. And in addition, you'll have this 2s plus 1 multiplicity. So you could have this as a sigma plus G state with a multiplicity 1. So which means only one combination of spins for this state. Or you may have a pi U with a multiplicity of 2, which means two spin levels, two spin combinations are possible for this state. Now, most diatomics, with perhaps just two exceptions, have a ground state which is a singlet sigma G plus. So the spins are up and down paired. So there's only one state possible, one spin state possible. The total angular momentum in the ground state is 0. The projection is also 0. It is a symmetric state, and it also has an inversion symmetry, which has an even reflection symmetry. So it is a Gerardo state. The only exceptions that are generally known to this is the oxygen oxygen molecule, which has a triplet state, and the NO molecule, which has a doublet pi as the ground state. And the doublet pi is essentially because the number of electrons in the outer shells of nitrogen and oxygen are not the same, and that results in one electron which is from the oxygen, whose outer electron is in the p atomic orbit, contributing to the angular momentum and giving a pi projection on the internuclear axis. Okay. All right. So what we have done. Well, let us quickly, summarize what we have done so far. I'll just run back through the slides right from the beginning and very quickly go through what we have done so far. What we have done so far is we started thinking of molecules as a collection of charged particles, in which the main difference between different particles is that there are two heavy particles carrying positive charge, and the electrons, which are much lighter, are going around these two or maybe more heavy nuclei. And then we saw that the potential energy of the system can be very conveniently thought of as being composed of three components: the rotational potential energy, the vibrational potential energy, and the electronic potential energy. Vibrational and rotational refer to nuclear motion, and electronic, of course, refers to electronic motion. The three can be separated essentially only because of the very large differences in the masses of the nuclei and electrons. And once this separation is done, unlike in the case of atomic levels, where there's no dependence on any other coordinate except the energy, uh, the energy levels for a molecule depend on the internuclear separation, and you get these nice looking potential energy curves with minima at different places for different excited and ground electronic states. The minima of each of these states correspond to the nominal bond distance in the ground state, excited state, second excited state, and so on. And whatever levels you see over here will correspond to rotational and vibrational motion. So we are not going to talk about rotational and vibrational motion today. This will be talked about by Vaibhav later in the day and maybe tomorrow. The important difference in the energy levels is that rotational levels are very closely spaced. Vibrational energy levels are somewhat more, have a somewhat larger spacing. And the electronic states, which are responsible for ionization, dissociation, and so on, they are actually much broader spacings. Okay, so milli electron volts, half a electron volt, and 5 to 10 electron volts. That is the typical scale. Then we looked at the electronic and the nuclear Hamiltonian for a simple diatomic molecule. And we looked at the different components of the uh, potential energy function. And then we started looking at different terms referring to the different conservation properties, different projections, different symmetries in the molecule, which result in an algebra or angular momentum algebra, which is somewhat similar to atoms, but not quite the same. The main difference being that in the case of atoms, there's a central potential. So the total angular momentum is a good quantum number. In the case of molecules, only the projection is a good quantum number, or the projected quantum, sorry, the quantized angular momentum projected on the internuclear separation, internuclear axis, that is a good quantum number. So based on that, we get different labeling of states. And these states are usually labeled by something like singlet sigma G plus or doublet pi U plus, etc. And most of the ground states of diatomic molecules have this kind of term symbol. Okay, now the term symbol doesn't tell us anything about the energy levels. Okay, the term symbol is simply a way of telling us what kind of symmetries exist for the electronic wave function. So the next job that we have is to start worrying about what the electronic energies, how the electronic energies are calculated, and what do we really mean by forming a bound state, because molecules are known to be stable and they are stable indefinitely. So the electronic energies of these molecules must have a minimum somewhere. How do we find these minima, and what do we mean by a bond? That is really what we'll try to find out. So in order to do this, we will have to solve the Schrodinger equation. And in order to solve the Schrodinger equation, we need to sort of simplify some things, or at least have a simplified notation for some terms that we're going to use. So here is a set of terms which I'll explain in a minute, which will simplify the writing of the Hamiltonian. So we'll call capital R as the internuclear separation, and it is simply the difference between the positions of the two nuclei A and B. Similarly, Rij will denote the difference or the relative position of two electrons, small r. Okay. Now, for a homonuclear diatomic, Ra, the position of the first nucleus, is simply half r, half of capital R, and the position of the second nucleus will be minus half r. Okay. Further, the nuclear charge on A is equal to the nuclear charge on B, which we simply call Z instead of Za and Zb. Now remember that when we write the position coordinates for the particles in a molecule. The very first picture that we saw, the very first slide that we saw. Remember that we are not interested in the motion of the center of mass. The motion of the center of mass is a completely different topic. It is really the kinetic theory of matter. Okay. So if you are describing the motion of the center of mass of the molecule, then you don't need to worry about these internal coordinates at all. You just need to describe the motion of the macroscopic motion of the molecule. And that is really the domain of the kinetic theory of gases. But what we are looking at is the motion internal to the molecule. Okay. So we are not looking at center of mass motion. You can assume that we are in the center of mass frame already. And in that center of mass frame, we are describing different particles inside the molecule. The nucleus is sitting at half r. So the origin of our coordinates is the center of the molecule. The other nucleus is sitting at minus half r. So with this simplification, the Hamiltonian becomes a slightly simpler, takes up a slightly simpler form. Has this electronic term, a nuclear term, and a somewhat long and complicated potential energy term, but now written in this new notation. Okay. Is this clear so far? What we are writing? I mean, the Hamiltonian, how the Hamiltonian is being written. Are there any questions related to the Hamiltonian or the terms, the term symbols?
No, sir, not till now.
Okay, all right. So now we come to, so it is important that you remember this, okay? So remember not as in the exact expression, but remember that there is an electronic term, there is a an electronic kinetic energy term, there is a nuclear kinetic energy term, there is a potential energy term, which describes the interaction between the electron and the nucleus. A second similar term describing the interaction between the electron and the nucleus. A third term, which is an electron-electron term only, and a fourth term, which is a nuclear-nuclear interaction term. So 4 terms in the potential and 2 kinetic energy terms. Okay. So yeah, we have already said that the center of mass motion is unimportant. That is not what we are trying to solve. And in a homonuclear diatomic molecule, the center of mass the motion of the nuclei can be described in the center of mass frame through a reduced mass, which is m1, m2 upon m1 plus m2. And in the case of a diatomic molecule, this will simply be half m. Okay. And then you can describe the usual planetary motion or central force type of motion in a space fixed coordinate with the origin at the center of mass to describe the nuclear motion, not the electronic motion. Okay. So if we do that, then this Tn operator, okay, so Tn operator is this kinetic energy operator. This kinetic energy operator, which is just minus half del squared n, n capital N standing for the nucleus, meaning the nuclear coordinates are being differentiated in this operator. And you would have also realized that the H cross is gone. Okay. Sorry, I should have put a mu here. I forgot the mu. So this becomes then minus 2 mu r squared. So this is like 2 mr squared in the case of atoms. And if you can recall your hydrogen atom problem, then this is like your angular momentum operator and the radial motion operator in spherical coordinate systems, written in a slightly different form for the motion of the nuclei. It is just the center of, just the motion of the reduced mass in the center of mass frame. K squared is like your L squared in the atomic units. Okay, so K squared is your angular momentum operator for nuclear motion in a space fixed coordinate system with the origin at the center of mass. Okay, so this is very much like your capital L in the case of atomic units, atomic systems. Okay, so at the beginning we said that a lot of simplification comes about because of this difference, which is written here in a different color. The mass of the nuclei is much larger than the mass of the electrons. So which means that all these terms, okay, so these Tn terms, or it doesn't make sense to talk of the value of an operator, but the eigenvalue of this operator, so if this Tn operator operates on the complete wave function of the molecule, Tn operating on psi n will give us energy eigenvalues for the nuclear motion. Okay. Now remember that this m is something like 10,000 times larger than the corresponding electronic term, which will have a me here. So me is 10,000 times smaller than mu. So the kinetic energy eigenvalue of the nuclear motion will be extremely small compared to the corresponding value when you're talking of electrons. So mu replaced by mass of electron. Of course, these terms will also not be identical, but just for us order of magnitude comparison, Tn will typically be 1,000 times smaller than electronic motion. And if you remember, right at the beginning, we had said this, that rotational or vibrational motion corresponds to much smaller energy compared to electronic energies. Okay, so that is exactly the point that is coming out of by comparing this operator with the electronic operator. Okay. So because this mass difference is very large, uh, just a minute, my screen has become a little garbled. Okay. So because because of this very large difference, what we can assume is that electrons are moving very rapidly and the nuclei are essentially stationary. So we can take the positions of the nuclei as fixed and describe the electronic motion occurring for a given position of the nuclei. So that is a very good assumption because of this huge difference in the masses. Okay. So the total wave function of the molecule, whatever it is, we don't know its form yet, but we can start arriving at certain structure for the electronic wave function, or we can start seeing certain symmetries or certain patterns that must be a part of the wave function because of this very pertinent observation. Okay, so because this separation is possible, or because this distinction is possible, the net wave function of the molecule must be a linear combination of the product of the electronic wave function and the nuclear wave function, because we are saying that they are essentially two separate things. They're just coupled by the potential, but the coupling is not very strong. Okay. So the nuclear motion can be written by a nuclear wave function. The electronic motion can be written by an electronic wave function. The net wave function is a linear combination of the product of such wave functions. But again, one has to be careful here. This R, which is the internuclear separation, also enters as a parameter for the electronic wave function. What does this mean? This means exactly what is written in the second point. We describe the electronic motion, which is this phi, to be occurring for fixed values of the nuclei, fixed positions of the nuclei. So which means that this R is fixed, you describe phi. So R is a parameter for phi, but it doesn't explicitly depend on that. Then this Fa, which describes the nuclear wave function, describes motion like the vibrational motion that we talked about, okay, or the rotational motion that we talked about. Okay? Those are all motions corresponding to a change in capital R. But this change is happening very slowly. And for every R, you will have a corresponding phi A. So when the nuclear wave function, the nuclear kinetic energy operator operates on a wave function like this, because this operator is a very sort of weak operator in some sense, and phi A corresponds to eigenvalues of energies which are very, very large, this operation of Tn operating on the product can essentially be taken to be phi A times Tn operating on the nuclear wave function. Okay, so the dependence of this on this is weak. So most of the action happens by the interaction of this operator on the nuclear wave function. So you have separated the electronic motion from the nuclear motion. Okay, when you're talking about the nuclear motion, you don't worry about the electronic motion. The electronic motion is happening at its own very rapid rate. So you are looking only at an average effect of the electrons. The electrons are very rapidly moving, and there's some slow motion of the nuclei. So the electronic motion is really smeared out. It's not like the nuclei are able to say, oh, here is an electron, and this is within my vibration, there is this electron here. That kind of a thing doesn't happen. The electron is very fast, and you start seeing an average effect. So the wave function is a product of the electronic wave function, and the nuclear motion, nuclear kinetic energy operator operates only on the nuclear part, nuclear part of the wave function. This separation or this approximation is called the Born-Oppenheimer approximation. This is a very important approximation. Because of this Born-Oppenheimer approximation, it is possible to separate electronic motion and the nuclear motion in this fashion, and then becomes the fun. The fun begins in the fact that now you can worry about calculating electronic wave functions without worrying about the nuclear motion. The only thing that you need to keep in mind is that whatever electronic wave functions you are calculating are for a particular value of the internuclear separation. For different internuclear separations, you will have a whole new set of phi. So it's a very complicated system still, but it is possible to, and because this separation is possible, it is possible to calculate these electronic wave functions for a given internuclear separation. If this separation were not done, or if this were not possible, then we would be faced with the problem of solving this very horrible looking Hamiltonian and trying to find some solutions to this H psi is equal to E psi kind of equation. Instead of that, we have now simplified our problem by saying that because of certain differences that we have spotted, the wave function must have a form which is a product product of nuclear and electronic wave functions and linear combinations thereof. And because of this very large difference in the masses, the nuclear operator operates on this wave function in this fashion. So the electronic wave functions can be separately calculated for a given internuclear separation. This completes the Born-Oppenheimer approximation. So what we are going to do next, maybe we can just take a 5-minute break. And we are going to then focus on how to calculate the electronic part of this total wave function, or calculate the electronic wave functions for some very simple systems. The nuclear motion part, which corresponds to, in our very first picture, corresponds to rotational and vibrational motion. That will be addressed by Dr. Prabhu Desai in his next talk. Okay. So in what remains, we'll be talking about the electronic wave function. So let us take a 5-minute break and come back in 5 minutes. And if you have questions, please keep writing them in the chat box. I'll have a look at the chat box.
Yeah, so attendees and participants, if you have any questions, either on the YouTube or on or within the Zoom, please write your questions in the chat box. So, Professor Bhas, they've had lectures on almost every subject, and we are ending this week with with molecular physics, and we are ending with solid state now. So, few days, and then on 11th we have our valedictory. So we have covered all the subjects of physics, both at the BSc as well as MSc level, giving them a kind of a revision.
Yeah.
And the wonderful part of your lecture is the clarity and the simplicity with which the molecular physics is being conveyed. It also gives you it's so nice. It's very nice. It gives you a feeling that yes, oh, it's so simple. And that's the point that is needed with every subject, the feeling that it's very simple and actually it's a very non-complicated thing, although the equations might look scary, but actually they're not.
Yeah, so yeah, with some simplifications it does become tractable, but in its full form it is certainly not tractable.
So there is a question from Priyoda that does fixing the R vector for nuclei means restricting the vibrational potential?
Yes, it does mean restricting the vibrational potential. So, but restricting so we'll come to this in a little while. So it is not really restricting it. What we are saying is that these are two separate, and we are separating the two motions. Okay. So what we are saying is that if I take a certain value of R, okay, which is the internuclear separation taken to be, say, whatever, 1 atomic unit, then for this 1 atomic unit, what is my electronic configuration? What are my electronic eigenstates? What are my electronic eigenvalues, energy eigenvalues? Then what I do is, so which we'll come to in a minute, then this energy actually feeds into the total Hamiltonian seen by the nuclei. Okay, sorry, it's total potential seen by the nuclei. Okay, we'll see how this separation happens. So what we now do is, for a given electronic state, we start calculating the vibrational energy levels. So it is not restricted, but it is done in a sort of what shall I say? Convoluted is not the right word. It is done with a feedback, let's say. So the electronic energy feeds back into the total potential seen by the nuclei, and for a given R, there's a certain E. That E feeds into the nuclear motion, and then you start calculating the vibrational motion, taking into account the electronic energy. Okay, so it is not restrictive, but it is done in a cyclic manner, if you want. And you calculate the energy, electronic energy eigenstates. That value goes into the vibrational, into the potential term for the nuclear motion, and then you calculate the vibrational and rotational states for that R. I mean, for that equilibrium value of R.
Thank you, sir.
So how many participants do we have? 80 on this. So are
We
they
have
from?
around
15 on YouTube as well, sir.
Okay, okay.
Yeah, so around 100 total.
Hmm.
And later on in the night and in the coming few days, they view it repeatedly on the YouTube.
Yeah.
So the number of YouTube views are more for network problems, internet problems, and also they have online classes till 7, some of them. So that's the reason. There is another question: molecular symmetry and energy states. How
Yeah.
do we relate them?
No, so as I said a while ago, the molecular symmetries and the term symbols that come mm, out of the symmetries, they are actually just additional uh, parameters or additional descriptors of the energy of the state of a molecule. They don't tell you what the energy is. So you can have a sigma state which is, say, 10 eV excited from the ground state. You can have a sigma state which is 5 eV excited from the ground state, and so on. So the molecular symmetry or the term symbols, they don't tell you about the energy at all. Okay, so the energies are calculated based on solving the electronic part of the Hamiltonian, okay, which we'll see in a short while. And if I may say so, I mean, it's not an entirely accurate statement, but it's a reasonably accurate statement. These symmetries are sort of, they're reflected through the value of the angular momentum, which we will not, I mean, angular momentum of the electrons, which we will not be considering when we calculate the electronic energy levels. So in some sense, these are two decoupled properties.
molecular physics courses must be being studied by the ISA students for their first year coursework of PhD, or?
First year course for PhD, as well as our undergraduate students in the last year. So
Yeah.
both set of students take the same course. Okay, shall we go
Please.
ahead?
Yeah,
okay.
we are used to having 3-hour long back-to-back sessions.
Okay, so
we are conditioned by now.
Okay.
Please continue.
Yeah. So let us now go a step further from the Born-Oppenheimer approximation. We said that we have separated these motions. And so let us now write down the electronic and the nuclear parts separately. Okay, so this is our starting point. That H is the total Hamiltonian. It acts on a wave function which is a product of electronic and nuclear wave function. So from this, if we now write this H as H electronic plus H nuclear and ignore the nuclear part, then the H electronic operating on this gives you an energy eigenvalue, which is what is called the electronic energy. Okay. So let me just turn my light on. Okay. So we separate the electronic and nuclear Hamiltonians, and since the nuclear operator has no effect on the electronic part, this equation becomes a very simple equation involving just an energy eigenvalue EA, which is an eigenvalue of the electronic part of the Hamiltonian. Now, what are the terms in the electronic Hamiltonian? So there is this T electronic, the kinetic energy operator, which is just minus half del I squared. And then this potential energy part, which has all terms except the nuclear term. Okay, so the ZA ZB by capital R term has disappeared from this because that term purely describes the interaction between the nuclei, which is not important for and which doesn't contribute at all to the electronic Hamiltonian. So the electronic Hamiltonian has one term less compared to the total potential. Okay. Now this R, which is appearing in this equation below, sorry, I'll have to again do something to my screen because this bar is bothering me. Okay, now I can point this. This term over here, R, is the internuclear separation. And you'll notice exactly what I just told you a little while ago, that the potential seen by the electrons is for a given value of the internuclear separation. If I change this R, V is going to change. But this R is not an R that is related to the electrons, it is related to the nuclei. So the potential energy term of the electrons indeed does depend on R, but not in an explicit fashion. Okay, so when I make any operation over here, this R will constantly stick out as a parameter. So E of EA, so the energy eigenvalue for the eighth state of the electronic wave function, electronic Hamiltonian, has to be obtained for each value of R. For any given value of R that you obtain, you will get a new EA of R. Okay. So the motion of the nuclei can in turn be considered to occur in the potential, which is defined by EA. Right? So that is how they are coupled. So EA is an energy, you could treat it as a potential. So take this EA of R, which has appeared because of the electronic motion, and plug this EA into the kinetic energy operator, into the potential energy operator for the nuclear motion, or the Hamiltonian for the nuclear motion. See, because you can treat it like a separation constant if you like. Okay. So this separation constant is the electronic energy, and you can then write the nuclear motion Hamiltonian, or the Schrodinger equation for the nuclear motion. So is this clear? So there is one term which is, one Hamiltonian, which is this, the electronic Hamiltonian consisting of these terms. And then there is a nuclear Hamiltonian, which consists of kinetic energy of the motion of the nuclei. Then there is the angular momentum of the nuclear motion. And then there is this separation constant, or the electronic energy, which is the coupling between the nuclear motion and the electronic motion. And this E over here is the total energy of the molecule. And this will contain electronic, vibrational, as well as rotational energies. So somebody had asked a question in the chat box about, are we ignoring vibrational energies? So no, we are not ignoring vibrational energies. It is, when I say that R is fixed, it just means that there is an equilibrium R for which we calculate the electronic energy, and that value is fed back into the nuclear motion, or the Schrodinger equation for the nuclear motion, and you calculate the vibrational or rotational energy corrections to this value, giving you the total E. Okay. Now let us go to a real molecule. Okay. So what is the simplest atom? The simplest atom is the hydrogen atom. Similarly, the simplest molecule is a molecular ion. It's not a neutral molecule, it's a molecular ion, which is the H2 plus molecular ion. It is the simplest molecule possible. It has 2 nuclei and 1 electron. Okay. So if you permit me to draw a diagram here, I'll just show you something. So it is like having 1 nucleus. So 1 nucleus. So this is a proton. There's another proton, and there's an electron which is moving in the field of these two. Okay. So that's my H2 plus molecule. So it's really a molecular ion. It is not a neutral molecule. So what is the Hamiltonian for this? It is a relatively simple Hamiltonian, which consists of one operator for the electronic motion, because there's only one electron. Then there is a potential energy term describing the interaction between the electron and one of the 2 protons and the other of the 2 protons. And then there is the 1 over R. Okay. Sorry, this is not H electron. This is the full Hamiltonian. And as usual, Ra and Rb are the positions of the 2 nuclei, and capital R is the internuclear separation. Now you might think that this H2 plus is a very exotic species. It is something that is very artificial. It doesn't exist in the, it might not exist in nature, but that is not at all the case. H2 plus is a very stable species, and it is found naturally in the interstellar medium. So a lot of work has been done to find out how the interstellar medium is, or what are the constituents of the interstellar medium. And it is well established that H2 plus exists in the interstellar medium. And it can also exist in the laboratory very, very comfortably. You can create H2 plus without any problem. And it stays stable for a very long time. Okay. Now, how do you obtain a Schrodinger equation for this Hamiltonian? So if we go back, what we have wanted to do is really solve this kind of an equation in which there is separation of the nuclear and electronic coordinates. So we are only going to solve this part now, where H electronic corresponds to the Hamiltonian for the H2 plus molecular ion, which is this term that you see on the slide now. Okay. Now, see, there is only one electron, and this electron is in the field of 2 nuclei. Now, in the case of the hydrogen atom, okay, when we wrote down this full Schrodinger equation, like this here, and this del squared can again be expanded in either spherical coordinates or some other coordinates. Okay. So you'll have a very long set of terms. We can try and solve this differential equation like we do for the hydrogen atom, but it turns out that it is not really very easy. I mean, it's possible, but it's not very easy. So at the end, we'll see how this can be done in an exact manner. But what we are going to learn today is really some techniques which are more widely useful, not just for H2 plus, but for other molecules also. So there is a method called LCAO, okay, linear combination of atomic orbitals, which is an approximate method for solving or obtaining the wave function, based, as is obvious from this term, on the linear combination of atomic orbitals. Then there is another method based on separation of variables, followed by numerical solutions. Okay, so this will very briefly look at. We won't spend much time on that, but we'll spend a little more time on this because this is a more widely applicable method, and it can be applied to larger molecules also. So this LCAO method assumes that this electron can actually belong to both these atoms. Okay, sometimes here, sometimes there, and in the separated atom limit, which means that if I move these two nuclei apart, then the electron will go and attach itself to either this or that with equal probability. And once this happens, the wave function of the electron to whichever of the two nuclei it gets attached to is essentially the same as what you would have for a hydrogen atom, a neutral hydrogen atom. Okay. But this neutral hydrogen atom does not have just one wave function, it has several wave functions, and it could be in an excited state or a ground state or whichever state. Okay. When they combine, and when the molecular ion is formed, this nucleus is no different from this nucleus. So the electron doesn't have a preference as to which nucleus it remains attached to. So we'll say that the wave function of this electron in the bound state or in the combined state is a linear combination of these atomic hydrogen wave functions. That's what this last point is. So we are going to need a lot of different kinds of wave functions. So let us write down some conventions. So if it is an atomic wave function, we will use the lowercase phi as a symbol to denote the atomic wave function. Now, a molecular orbital wave function, which is the wave function that we just talked about, which is formed by a linear combination of atomic wave functions, will be denoted by an uppercase phi. So this is a lowercase phi, this is an uppercase phi. This is not to be confused with the angular momentum projection. It is also not to be confused with the azimuthal angle. Unfortunately, one starts running out of symbols, and phi is a very commonly used symbol here, but that can't be helped. Now, a molecular wave function, which is formed by a linear combination of these kind of wave functions, is, see, just as the complete wave function for a hydrogen atom is a linear combination of its different 1s, 2s, 2p, and so on wave functions. The net molecular wave function will also be a linear combination of these phi's, and that we denote by uppercase psi. Okay, so let us go back to the electronic motion in H2 plus and start writing linear combination of atomic wave functions in order to depict the molecular orbital wave function, not the molecular grand function, but the molecular orbital wave function. Okay. So if this electron, there's only one electron, if it belongs to atom A, we will call it phi r of A. If this electron belongs to atom B, then we'll call it phi r of B. And when I say belong, it just means that this belonging is in the sense when you start separating the two nuclei. In the separated atom limit, this wave function would represent the case where the electron went and attached to atom B, nucleus B. And the other one would describe the case when it went and attached to nucleus A. But of course, you can have this with the minus sign because it doesn't change the energy of the system because all energies are related to the modulus square of the wave function. So this doesn't change sign. And you can have two different linear combinations with the same energy. One of these is called the phi, not the same energy, but the same symmetry. So one of these is called the phi g function and the other is called the phi u function. And they are called G and U simply because if I change RA to minus RA and RB to minus RB, these will change sign. and that is really the meaning of G and U. So in the first form, as I just said, there is a symmetric wave function. In the other form, it is an antisymmetric wave function. Okay. Now, in writing these phi's over here, we said that these are wave functions of the hydrogen atom. But when we say wave functions of the hydrogen atom, these could be 1s wave functions, 2p wave functions, 3p wave functions, whatever. They have to be hydrogenic, that's all. But if phi are all 1s hydrogenic states, okay, then the net wave function, which is this capital phi that we have written, this wave function corresponds to L is equal to 0 state. So both phi g and phi u are states in which the angular momentum state is a sigma state. Now remember that I would normally have used a capital sigma, but here I'm using a small sigma because there's only one electron. There's no sum of projections of angular momenta involved, which is normally the case for a molecule. Here there's only one electron, and sigma refers to a zero projection of the angular momentum on the internuclear axis. They are doublets because there's only a spin half possibility. A spin half just means either an up or a down. So there are two states, two spin states. That's why a doublet. So if you calculate these wave functions, very simple wave functions. The only thing to remember is that you have to calculate these for different, refer to different internuclear positions. And once you do that, you get these two wave functions. The purple wave function is the G state, which is the even state. And as you would expect, it has a symmetry. The other one is antisymmetric under inversion, and that is a U state, and it has a shape where the wave function goes to a negative value for the left half and positive value for the right half, and it has an inversion antisymmetry. If I take the mod squared of this, okay, mod squared of this wave function, which then becomes a function which is proportional to the electron probability density, then the G state, which is the antisymmetric state, sorry, other way around, has a very sharp maxima at the locations of the nuclei, and the G state has relatively shallow maxima at these locations of nuclei. But the density of electrons at the midpoint is very high for the G state. Okay. So which means that this G state, the electrons are more likely to be present in between the two nuclei, and hence this is expected to be a state which is more strongly bound. Okay. The other one, the green state, has zero density at the midpoint, which means this is going to be of a higher energy or greater or less stability, because if the electron is nearly absent from the center, from the midpoint, then the repulsion between the nuclei is going to tend to make the bond weaker. The nuclei are going to try and move away. Okay. So the green state corresponds, or is expected to correspond to a higher energy, less binding. The purple state is expected to have greater binding or a deeper minimum. So how do you calculate the energies? Because that is what we want to know. If you can calculate the energies, we can talk about bonds and bond energies and so on. So in any case, in both cases, you can calculate the energy by simply finding the expectation value of this H, normalized to the normalized in the usual fashion. Okay, once this is done, then you can write this term, expand this out, and you will get different terms in this expansion. Of these, EEAA, which is this term, or EBB, which is the same thing with A replaced by B, is one kind of term. And there is a EAB or a EBA term, which is like this, which is again I mean, the EBA term is again something very similar. And then we also define something called an overlap integral, okay, which is just the integral of the wave function centered on A and the wave function centered on B, and the overlap density of these two. Okay. So this is usually called the overlap integral. So some of these integrals are defined in order to simplify our algebra in calculating this E. So with these definitions, EAA takes this form, and EAB takes this form. Then the denominator, which is the normalization factor, which is this part. The denominator again involves the S, okay, and depending on whether you have phi A plus or minus B, sorry, whether you have the G state or the U state, where is it? Yeah, whether you have the G state or the U state, you'll have a plus or minus sign, and that is also again appearing in this normalization integral. We put in all these numbers, calculate these energy eigenvalues, and you get E, G, or EU is given by this long expression. Okay. And E naught is simply the binding energy of the electron to one of the nuclei, which is really the hydrogenic binding energy. Okay. So if phi A and phi B are 1s states, then E0 is are actually minus 0.5. These are all negative numbers. I have not shown the minus sign, but these are all negative numbers. So E0 is minus 0.5. Now the EG and the EU, okay, if you look at this expression carefully, they are all, I mean, both these expressions are functions of capital R. This is the point that I was trying to explain earlier, that the electronic energies are calculated for a given value of R. And then for different values of R, I'll get different energies. And since there's only one electron to worry about, this calculation has been quite simple. And with this, we get these two E of R curves. The purple curve, which is the G state, which has a lower energy. There's a U state, which has a higher energy. And if you look at this carefully, the U state does not have a minimum except at the asymptote. Okay. So the U state corresponds to a configuration in which there is no energy minimum at any finite internuclear separation. Whereas the G state has a minimum at something like 2.4 or 2.3 atomic units. And this has a binding energy of about 0.04 or something like that. Okay, 0.06. So this is a very crude calculation. Okay, this is a very, very simple way of showing electronic bound states. But you will see that even with this very simple calculation, you get one state which is a bound state and another state which is a repulsive state. So these numbers that we are getting are very crude numbers. They are far away from reality. But this method illustrates the principle that if you start with something which is very simple, like a hydrogenic wave function over here, do a linear combination, you can still identify some very, very important and very significant features in the molecular wave function. So are there any questions here? Okay, so let us go ahead and let us now look at.
So there is one. Can you explain about the right side of the plot? She says.
Can I explain the right side of the plot? This side.
Yeah, right side of the plot.
Okay. So if I so remember that these functions are drawn based on this expression. So as I go to larger and larger internuclear separations, that means that the two nuclei are being taken far apart. These two are going to merge. Okay. So that essentially represents the case when there is no interaction between the two species and their total energy is zero. Zero meaning The internal energy is zero. They could have a translational motion, that is a separate thing. But their total energy, total internal energy is zero. And that would be when these curves are taken to the asymptotes. Is that clear?
मूंगफली तो
Okay. So
there is this uh, um, for this molecule only ground state is bounded.
yes. There's only one bound state. And I mean, even so let me explain this further. See, this crude calculation, this very simple calculation shows that there is one bound state and the next state is an excited state. It turns out that this molecular ion actually has only one bound state. Okay. So any excited state of H2 plus is a repulsive state, and that is amply shown even by this simple calculation. Okay. So there's another method which involves separation of variables in order to calculate the electronic motion. So I'm not going to describe much of this. I'm only going to show you that such a thing is possible. So you define new variables called zeta, eta, and phi. So phi is just the azimuthal coordinate with the internuclear axis as the reference axis. And xi and eta are two new coordinates. They are called confocal elliptic coordinates. So they represent, if you look at this carefully, they represent the combined motion of the electrons, or sorry, the combined position coordinate of the electron scaled to the internuclear distance. And this is in some way the separation between the two electrons, again scaled to the internuclear distance. So these are both, on all three of them are dimensionless quantities, dimensionless coordinates. And if you write down the electronic Hamiltonian in these transformed coordinates, it becomes possible to write three separate equations, which are of this form. Look quite complicated, but the azimuthal equation comes out very nicely. This is what you would expect. The projection of the angular momentum on the internuclear axis is a conserved quantity, and because of which you have this very nice and simple equation for the phi part of the Hamiltonian. You'll simply get e raised to im phi kind of solutions for this last part, which essentially tells us that the projected angular momentum is a conserved quantity and is a good quantum number. These are more complicated. You get two more sets of quantum numbers, but we are not going to get into this. It's too hard to do. But we'll now go over to a slightly more complicated molecule itself.
Sir, there's a small question.
Yeah.
From the curve you represented, that it represent the second order potential if then any relation is there Laplace.
Sorry, no, I didn't get this question.
So this curve represents the second order potential if then is there any relation with Laplace?
Laplace what?
Veer, can you elaborate your question?
So I think he means that this curve is representing a second order potential.
No,
If this is
what does
true,
second order? No, what does second order potential mean?
I mean, I'm reading out his question.
Okay.
Then if then any relations is, so does it have any relation with the Laplace what equation or what?
Okay, so see, the Schrodinger equation and the Laplace equation for charged particles, they have a lot of similarities. I mean, the angular part is similar, but the radial part, of course, is not. But the angular part is very similar. So in that sense, there is a similarity. But if you recall what we did earlier, we have separated the nuclear and the electronic wave functions. Now, for that Hamiltonian, you will have I mean, that meaning for the nuclear Hamiltonian, of course, you will have those angular momentum terms and so on. But what we are doing here now is a slightly different game. Okay, what we started off with is we started off by saying Now, I presume that your question is related to these potential energy surface curves that I have drawn, not anything else. So assuming that, let me just quickly recapitulate what I said. So the molecular wave function is written as a linear combination of atomic wave functions in a certain fashion. And then the energies of, sorry, not first the energies, first the wave functions are calculated based on this linear combination of atomic wave function. Okay, so two wave functions emerge, and those wave functions are plotted here. So phi of r for the G state and the U state. And then what is plotted here is also the probability density, which is essentially the probability of finding that one electron. There's only one electron in the system. And you see that in the U state, the electron is not going to be found in the gap between the nuclei. So this is represents a state where the repulsion between the nuclei dominates. The other state is the one in which the electron is more likely to be found in the center. So this electron does the job of keeping the nuclei together by its attractive force. And as a result, this is likely to be a more stable system because of the increased electron density at the center. Based on this, we calculated an energy which is a function of, I mean, it is integrated over Ra and Rb, but it is still a function of the internuclear separation R. And that is what we have plotted here. As a function of the internuclear separation, the total energy of the system is, I mean, either follows this curve or it follows this curve, depending on which of the two linear combinations of atomic orbitals are included in the wave function.
Sir, he has written that the del square is actually equal to rho by epsilon, that is our Gauss
Oh
law,
my
and
God.
not E by R is equal to del square.
No, del squared is only an operator. Del squared is not a physical quantity. It's an operator which operates on something. So what you are getting confused with is del squared or operating on the potential energy function gives you rho by epsilon.
Okay,
It's a
sir.
potential, it's an electrostatic potential alone. That's all.
Yeah.
They are not moving charges. They're just, that's a collection of charges which are not moving. It's electrostatics.
Yes. One question is from Priyoda, sir, that in separation of variable method, have you considered two electron system?
No, no, we're still on the one electron system.
Okay.
So this equation, this is still for H2 plus. It is a one electron, two nucleus system.
Okay.
So in some sense, this is the exact inverse of a helium atom. There are two nuclei and one electron, whereas in the helium atom there is one nucleus and two electrons.
Yes. Thank you, sir.
But this separation is possible because of the Born-Oppenheimer approximation, which of course doesn't apply in the case of the helium atom. Okay, so let us go to the last part, which is how to find the electronic wave function for H2. H2 is the next uh, complicated, if you like, molecule, but it is still the simplest neutral stable molecule. So we are really at the bottom of the ladder, and then you can see that this is already quite hard. Okay, so calculating exact wave functions is a very, very hard job. So what does the electronic Hamiltonian look like for H2? So again, we use the same notation as before. Simpler notation does not involve Zs. It simply involves the del 1 squared, which is the kinetic energy operator for first electron, kinetic energy operator for the second electron, then the 1 over R1a term, the interaction between the first electron and the first nucleus, interaction between the first electron and the second nucleus, and so on and so forth. Then the electron-electron repulsion term, then the nucleus-nucleus repulsion term. Unfortunately, in this case, not is not not is it just not possible to solve this exactly, but even a separation of variables cannot be effective, unlike the H2 plus. So just in order to keep our bookkeeping somewhat simpler, we break up this Hamiltonian into slightly simplified notation. It is just the same Hamiltonian, but we write it as H naught 1 plus H naught 2, and clearly H naught 1 means terms which involve 1. So this, and this term. H naught 2 involves this, and this term. Okay. So H naught 1 plus H naught 2 plus 1 upon R1 2 plus 1 upon R1. This is just for better bookkeeping. All right. So what happens next? We have this Hamiltonian, and like we attempted writing the
Sir,
okay,
you
yeah,
are
yeah,
muted. Yeah.
I'm back. Yeah. So to solve the H2 plus problem, okay, H2 plus problem, not the H2 problem. To solve the H2 plus problem, we created a linear combination of atomic orbitals to create a molecular orbital wave function for one electron. Okay, I hope this point is clear. We started with an atomic wave function. We did a linear combination of atomic wave functions centered on two different nuclei. The linear combination was resulted in a wave function for an electron moving in the field of two nuclei. So essentially a molecular orbital wave function for one electron. We are now going to use this molecular orbital wave function for one electron to describe a multi-electron atom. So do a linear combination once again, but linear combination of molecular orbital wave functions. So we write a trial solution based on the wave functions of H2 plus. We take the trial wave function to be a linear combination of H2 plus molecular ion wave function. So we're building up step by step. We first built our first block, which was the H2 plus wave function. Now we're going to build the H2 neutral wave function, which has two electrons, by writing a linear combination of H2 plus molecular orbital wave functions. And of course, there will be spin parts which are separate from this, but they will come as products. Okay? But because there are two electrons, we need to worry about the spin business somewhat more seriously because of the Pauli exclusion principle. So for two electrons, the Pauli exclusion principle says that you can either have a singlet where the spins are opposite, or you can have a triplet where the spins are parallel. So remember that if you have this configuration, you have a symmetry. If you have this, you have an antisymmetry. So if I write the spin wave functions for these two electrons in terms of up wave functions and down wave functions, then just the spin part. Okay, we are currently talking only about the spin part. The spin part for a 0, 0 type of, which I call 0, 0, which are basically the projections, would correspond to a linear combination like this. Alpha means a spin up and beta means a spin down. So you can have one up, two down, or one down, two up. So total S is 0, M is half or minus half. You can similarly have a 1, 0 wave function which has spin up for one, spin down for the second. Wait a minute, I think I made a mistake here. This should be 1, 1 and 2, 2, okay? Should be 1, 1, 2. And then you should have, then there'll be two more functions, which will be both spins up and both spins down. Once you write down these four combinations, then the spatial part and the spin part combined should have the required Pauli exclusion antisymmetry with respect to exchange of the particles. Now, there are two molecular orbitals from which we can choose. If you remember, these were the molecular orbitals of H2 plus, which we had constructed based on linear combinations of atomic wave functions. So small phi, lowercase phi are atomic functions, uppercase phi are molecular ion wave functions. So this is symmetric with respect to exchange, this is antisymmetric with respect to exchange. it picks up a minus sign when you exchange the particles. So the grand wave function for the 2-electron molecule will have combinations like this. Okay, so for S is equal to 0, you can have this psi 1, which consists of phi g1, phi g2, psi chi 0, 0, phi u1, phi u2, chi 0, 0. Okay, these are S is equal to 0 cases, or this last case. And there'll be only one possibility for the triplet case, which is that this triplet wave function can only be of this form. Okay. But there are 3 sub-levels over here. So this psi 1 represents the lowest state because phi g is what we have chosen to form this. And sorry, this should have been capital phi u, not small phi u, because phi g is the lower energy molecular orbital. So 2 molecular ion orbitals combining to give the 2 electron psi will have a linear combination of phi g's. Okay. So this total energy of the system will again be calculated in this same fashion. Psi 1 star h psi 1 integrated over now 2 electron volumes. Okay, so delta 1, delta 2. And this will then, if you expand this out, it will turn out to be of this form, where Eg is the energy of the G state in the molecular orbital, which we had calculated earlier. Okay. So once you do this integral, which has to be done numerically, you end up getting these following values of energy. Okay. So this is called DE for a different reason. I'll tell you what. So it is essentially the binding energy. It turns out to be 0.1 atomic unit or 2.7 eV. So this is even lower than what we had seen earlier for the molecular ion. Okay, so if you remember for the molecular ion, this energy was only 0.05 or 0.06. For the molecule, this energy is even lower. It is 0.1. So these are all negative numbers. It should be minus 0.1, minus 2.7, and so on. So you get a dip in the wave function, which has a depth of 2.7 eV. Okay. Sorry. Now, what is the approximation we have made here? We have said that we start at the phi g state only. We take only the linear combination of phi g's. Now, that is obviously an approximation. There is no reason. I mean, if this is a complete basis set, then this is a linear combination of all possible vectors in that basis set. But we have only taken one of them, or rather 2 of them. Now you can calculate this energy for different values of R, or not. Yeah. Now R0 is the value of R for which this energy turns out to be the lowest, and this is 0.8 atomic units. So this means that the binding energy of this H2 atom, this very simple or crude H2, not atom, H2 molecule that we have constructed, has a bond length of 0.8 atomic units, and which is the same as 1.5 AV atomic units, and it has a binding energy of 2.7 eV or 0.1 atomic units. Now both these numbers are quite far removed from reality. The binding energy is actually 4 point something over here, and this is about 1.1 atomic unit, 1.1 angstrom or 0.98 angstrom, something like that, but it's larger than this. So on both these counts, our approximation is somewhat removed from reality. And there has to be a slightly better way to do this whole problem. Okay. So let us just look at what we are missing. Okay. So what I've done over here is I have expanded this in terms of all atomic combination, all atomic contributions. Okay. So this psi I12 is a sum of products of various pairs. So this first term represents the case when both are 1s. This is again the same 1s but with an exchange. Then this is a 1s in which both atoms are attached to this nucleus A. And the second one is a case where both electrons are attached to the nucleus B. So this term as well as this term, okay, really represent the case when one nucleus has captured both electrons and the other nucleus has no electrons attached to it. So both electrons are very tightly bound, both electrons are very tightly bound either to nucleus A or very tightly bound to nucleus B. Now, in this wave function, if you look at the coefficients of each of these terms, the coefficients are all 1. So which means that all these possibilities have been given the same importance or the same weight. But we know that this kind of a case where there is both electrons getting attached to this to one is a bit of a exact. I mean, it's not such a strong possibility. We know this intuitively, and we can also do this based on how the electron might be distributed if you were to just take one electron. So this is really what is called the covalent component. This is called the ionic component for obvious reasons, because when both electrons go to one get attached to one nucleus, it acquires a negative charge and the other one acquires a positive charge. So this becomes ionic bonding, whereas this becomes covalent bonding. So what one could do is, one could just say that there is a certain part. Okay, I think I'll not go into details now. We're getting late a bit. So the second two terms, which are the ionic contribution, and the first part, which is really the covalent contributions, they can have different weights or they can be combined in different forms. And if you do that, if you do that and combine these with some coefficient such that these four terms over here are not added with the same weight. So these two terms are added with a higher weight than these two terms. In that case, what happens is you start getting energies which are slightly more complicated functions of these various integrals. And these integrals really represent different kinds of overlaps, some kind of exchange. And they're essentially integrals of two wave functions overlapping with different nuclei being involved, or different or electronic wave functions centered on different atoms in the molecule, and you get these three terms. So all this, I think you'll have to work out in order to follow this. It's a little complicated, but it turns out that this energy, the total energy, can be written in a relatively compact form in terms of these integrals. Okay. And then you can, once you have these values of j, k, and I, these three integrals, the energy can be calculated again for a given value of r. All of these involve a certain value of r. So, all these improvements based on some kind of a linear combination of covalent and ionic bonding with different weights can lead to a better and better estimate of the total energy. Now, if you remember the variational principle, the variation principle takes you to the minimum energy by finding out the value of the variational parameter, which will lead you to the minimum. So a similar thing can be done by mixing psi1 and psi2 wave functions, which we had described earlier, which have the same symmetry but have different binding natures, and try to minimize the energy for this, the total energy for this combination, by treating lambda as a variational principle. Okay. So various such combinations, some trial wave functions and so on, can be worked out. And with all these trials, one can get a slightly better estimate of the binding energy. Okay. So in summary, what we have, okay, so before you go to summary, let me just go back to this. Maybe I have this, yeah, okay. Sorry, there's some change in the order. So this is what is, these are different potential energy curves calculated for all these four linear combination of these four molecular orbital based wave functions with different curves representing the four different possibilities. One of these, which corresponds to the lowest bound state, is about 4.7 EVD. These are reasonably exact calculations, or almost exact calculations. So 4.7 EV is the binding energy. Okay. And in the this is this will have about 4.7, and the bond length, which is the position of this minimum, appears at about 1.2 angstrom. So in summary, whatever we could do today, whatever we could go through today, is something like this: that electronic and nuclear motion in molecules uh, is combined, but because there's a huge difference in the masses of the nuclei and the electrons, the two motions can be separated, and we can describe these two motions uh, in a separated form. Okay, so with some separation constant, which is the energy of the electrons, I mean the electronic part of the energy. And electronic energy levels are very widely separated. So for a given value of E of R, you can calculate small corrections to it, which are essentially the nuclear vibrational and rotational energies. And you then start constructing these curves, which we have shown a few times in our discussion, which are the potential energy curves. The energy as a function of R, which is obtained from the electronic wave function calculations. On top of this, there is a nuclear energy, nuclear rotation and nuclear vibration component, which will be talked about in the next talk or tomorrow's talk. Okay. And this way, by separating the total energy into nuclear rotations, nuclear vibrations, and electronic motion, we are able to gain an insight into how an atom, how a molecule is constructed or is formed. And it also helps to think of linear combination of atomic orbitals to understand in a very simple or a crude manner the stability of molecules. Okay, with this I'll stop. And if there are any questions, I'll be happy to answer those.
Thank you so much, sir, for this wonderful talk. Students, if you have any queries, any doubts, please write either on YouTube for YouTube viewers and on Zoom chat box for Zoom attendees.
Students, please be fast in asking any questions if you have them in mind. There are none.
Okay.
So either everything was absolutely clear or everything went above the head. But I can say that these are very good students, and they have been very, very regular in the past almost 3 months. And I'm sure, as I felt, they have felt too, that your talk was very simple and accurately delivered to point out the details where we must dwell upon while understanding this particular subject. So I really liked your talk, and it was very nice. And I wish you had more time to give us for molecular physics, but maybe next time in another series.
Yeah, sure.
So thank you so much, Professor Bhas. And it was really a pleasure for me personally. And I'm sure the students are thanking you profusely on the chat box, if you can see after stop sharing your screen.
Okay, I'll do that.
You
Okay,
have to
so let
stop
me
sharing
stop.
in order to see
I'll stop
compliments.
sharing.
You cannot share and see
I know.
simultaneously. So as you can see, they are thanking you. You made difficult concepts very easily. That's his speciality. He's known for speaking the toughest of the things in the simplest of manners in molecular physics and so on. Maybe we'll have the pleasure of hearing him again in some other series. So thank you so much, Bhas, and I'm
Yep.
really grateful that you took
Okay.
out
Thanks.
time.
Thanks, Punita, for inviting me.
Yeah, thanks to Nasi, which allowed us to hold this series for the
Yeah.
benefit of the students. It started at the time when there were no classes being held, and
Mm-hmm.
now universities have opened up. But the students have persisted, and that itself is a compliment that the hard labor of the
Program
teachers
is
is
going on well.
reflected.
Yeah.
Sure, sure. And now we have
Okay.
also our next speaker, Vaibhav has joined. So really, thank you once again. I really
Okay.
wish you
Bye.
had 6
Bye.
days
Yeah.
to 6 days to
Hi, Vaibhav.
uh, Hello, Vaibhav.